Okay, so here's our do now. It's similar to yesterday, but some important differences. And I'll give you 3 minutes for it.
I was having trouble with like this, like making an equation for it. Like how can you explain?
So talk to at your table right now, and then we'll kind of go over it as a class. Just like yesterday, but yeah, it's a different. Just
Would it be P of M or
P of T. All right, so use the example from yesterday to help you. Okay, what do you have to calculate about this graph, and then where do you write the numbers?
V, right?
What should we use today? Position is X. Yep, so there are some similarities and some differences between the one yesterday and the do now today. If you're unsure how to get started, at the very least, you know you need the slope and the intercept. So you should be able to do that, find the slope and intercept of this graph. So if you're not sure how to start there. Sit right there. Yep. Is anyone sitting here? Okay, sit down. I'm hearing some good conversation, so let's take another minute. So it's a different unit for your slope this time.
Because position is X.
So position is measured in meters. So the y-intercept should be in meters, and then your slope should be different too. Okay, so how do you want to get started with this question? Melanie, what do you want to do first? Yeah, what would the slope of this line be? So it's going down 3, so that would be like negative 3 meters. And what would 4 seconds? Okay. So our slope is, you can write it as like negative 3/4 or negative 0.75 meters per second. Whoa. I'm fine. Whoa. Yeah, I'm fine. Whoa. I'm okay. I'm totally okay. Just a little surprised. Wow, that physics is crazy. All right. I'm just like really excited for physics. Whew. Okay. Focus, focus, focus. Okay, so that is the slope. What about the y-intercept? What should the y-intercept be for this graph? Okay, so it's 5, but 5 what? Meters. Okay, how is this different from yesterday's example? Marilla, how is it different?
Yesterday, the position was like meters per. No, it wasn't position. It was meters per second, like meters per second.
Why? Yeah, why was the units yesterday different than the units today? Right, because today we are doing position versus time, and yesterday we were doing velocity versus time. Okay, awesome. Now we know, what should the equation of the graph look like? You missed something very exciting. You'll just have to have everyone else tell you. Okay, so what is the general equation? Y equals mx plus b. Yeah, so let's start doing our substitution. So we already know what the slope and the y-intercept is. So negative 0.75 meters per second. And then our intercept would be plus 5 meters. What variable should we replace x with? T. And what variable should we replace y with? Yajali? V, P, X. Okay, it's okay if you wrote P, just X, because it's the variable, not where we started. So actually, you could also write it as X of T. What would P if we were writing this as variables? V M would be V0 and B would be X0. But because we have a specific graph, we replace it with the numbers. But we still leave the variables. We still leave X as a function of T and the T.
So the position is going to be S of T.
X of T, yes.
And if it's velocity, it would be
V of T. And if it was acceleration, it would be A of T, right? So those are the different graphs that we've been looking at over the past 2 days. So what I'd like to do today, first, I'd like to not fall again. And then second, I would like to show you how to, you've already been doing some examples of this on your homework, right? I want to go through in some detail how you would solve a question. And then you're going to, in your groups, you are going to make an explainer video on how to solve a question. So we'll talk about how you're going to do that in a second. First, we need to talk about the different equations. So if you have your reference table, I want you to turn to, or just, you can just look at it at your table. Everyone doesn't have to pull it out, but the last page of the reference table, page 6, has 5 equations at the top of the reference table there. And those 5, I just want you to see where you'd find them, but these are the 5 equations that are at the top of the reference table. So you turn to the last page, page 6, and it's the 5 at the top. So these are just some names. You don't have to copy this part down. We're going to copy down the next chart. But this is kind of giving you an idea of what these different equations represent, right? The first 2 being the definition of average velocity and average acceleration. Then we have 2 equations, velocity as a function of time, position as a function of time. And then this last one that's kind of new, we'll talk about where it's useful in a second. The other things I want to remind you of, you don't have to memorize what any of these letters stand for, right? That list on the right side just has them all listed, okay? Now, these are the equations that are on the reference table. These are, you know, they're nice equations. I like them. They're okay. But I don't really think they do a good job representing what they mean. So in our notes, we're going to write down different equations. You can also write them on your reference table as well. But I want you to know this is what you're going to see in June in the blank reference table that you get. But these are the 5 that I want to look at. They're connected. You can see the similarities and the differences. So I want you to make this chart. This is the one I want you to copy down. Make this chart in your notes. Okay. So it's 4 equations instead of 5 because we combined 2 of them. If it's not refreshing on your page, just like hit like the refresh bar. It should refresh. Just give it a second. Okay. So our first equation is velocity as a function of time. Position as a function of time is our second equation. Velocity as a function of position. And then this is like a bonus one. This one combines sort of velocity and time, but without the acceleration. You can see the similarities between the second and the third, like where the half shows up. And you can kind of see like this VIT piece as well. Okay. What I want to mark off is which variables are found in which equations. Because that's a really important thing to know when you're trying to know which equation should you use to solve a problem. So in our first equation, we have V final, V initial, A, and T. So any question that has 3 of those given and 1 of those unknown, you could use this equation to solve. Okay. The second equation has X final, X initial. It has V initial. It has A, and it has T. Okay, so everything but X final. Okay. The third equation has V final, V initial, A, and delta X. And the last equation has delta X, V initial, V final, and T. Okay. So again, depending on what you have and what you want, that's how you decide which equation that you're going to use. Remember, X final you get by doing, change in X would be X final minus X initial. So that's where that comes from. Try. I'm going to try. Oh, no. I'm trying to update the thing there. I think when I fell, it just freaked out. All right. So is it showing up on your screens now? Yeah. Perfect. Yeah. So mark off those checks. So this gives you an idea of like which equation would you want to use depending on sort of what you know and what you're trying to solve for, right? And we're going to do an example together, and then that's what you're going to work on in your groups. Now, it's possible that when you're solving a physics problem that you might need to use like more than one of these equations, right? Two equations, 2 unknowns kind of idea. But for all the questions that you'd see on a quiz, test, or the Regents exam, you'll only have to use 1 equation, right? It might be possible to solve it using 2, but you won't have to use 2. If you pick the right one, you'll only need to use 1 equation. So I'll give you 30 seconds at this. Again, the check marks you can see for yourself just by looking at the equation. All we've done is mark off which variables are or aren't in that equation. The other thing to think about is like what happens when some of these variables become 0. So like for example, if the acceleration equals 0, this part goes away and we get X final equals X initial plus VI times T. We just use that equation to do the do now. This equation's not that interesting. This one just says v initial equals v final. But that makes sense. If we're not accelerating, that shouldn't change. Same thing if we make a equals 0 here, we just get v final equals v initial. Again, that's not new to us. We would expect that if the acceleration is 0. Okay? And of course, you can take any of these equations and algebraically change them to suit your needs. So let's say you wanted to take this first equation and solve it for a. You could get a equals v final minus v initial divided by t, for example. Okay, and you'll get some practice with that over the next week. The other thing I want you to notice is letters show up in more than one place. Right? How many equations have the acceleration in it? 3 of them, right? So you want to keep in your mind separate equations that have acceleration in them and the definition of acceleration. We said that the definition of acceleration is the change in velocity divided by the change in time. Likewise, we said the definition of velocity is the change in position divided by the change in time. It's a subtle difference. So far, most of the equations you've been using has been with the definition. Like the acceleration homework said, the velocity was this, then the velocity was that. It took 4 seconds. What is the acceleration? That just uses the definition. But let's say you were told how it was moving and how much time it took and what the initial velocity was. That's the kind of question you would need to answer with one of these other equations. And that's something the more you practice, the more you'll get an eye for. Should you be using the definition or should you be using these equations? And they're connected, okay? So take another 10 more seconds, copy this down. Mr. Sampone, what's up? So that's something that you'd have to add to the as you go along. You should have access to be able to edit the form. So you just go to where the list is and you just like put in CA2. Okay, I'll get an updated list from Melissa on who's enrolled in the classes. Yeah, you're welcome. Yeah, so let's look at an example now of the kind of question you might have and how we would solve it using the guess method. Okay, so here's our question. A softball initially traveling at 35 meters per second takes 0.25 seconds to be caught by the catcher. What is the acceleration of the softball? Okay. So here's Fiegel playing softball, catches the softball. Fiegel? Y'all know Fiegel? That's right. I believe so. Okay. It's not moving. Oh. Try just like refreshing the. All right. So we want to go through this question and we want to write down we're just going to have to be patient with the technology. Okay. So we need to start with the givens, then the unknowns, the equation, the substitute, and the solve. Okay. So what was a piece of given information in that question?
35.
Okay. So V initial was 35 meters per second. What else was given in that question? Yeah, let's jump back. Okay, so the time. Okay, is there anything else that is given in this question? Okay, we can write that down. So we can add that as our unknown. We're trying to solve for the acceleration. There's one more thing that's given to us. My hint is it's not given as a number. Melanie?
Is it the part where it's like initially?
We already used that when we said VI equals 35. Which part, Sean? What would its velocity be when it's caught by the catcher? 0. So this is an example of what we call a hidden given. So V final equals 0 meters per second. So here's what you need to do now. You need to figure out which equation has V initial, V final, T, and A in it. Yeah, that first one does. So VI equals V final plus A times T. We looked at our givens and our unknown, and we're trying to find the equation that has those 4 things in it. We caught because when we catch the ball's not moving anymore. So you have V in, I switched it, you're right. It's V final equals V initial plus AT. Thank you. So now the next thing we would do, because we are expert physicists, we would solve this algebraically for the answer. So I would move V initial to the other side. So I have V final minus V initial equals AT. And then I would divide each side by T. So A equals V final minus V initial divided by the time. A and T are being multiplied, and then it's being added, right? And it's being added. Okay. So now I'm on the substitute. So V final, yes. How do I know what? How do I know it's this equation? We looked at our givens and our unknown, and we picked the one of the 4 that has all the things we need. So now I can do this substitute. So V final is 0. Then minus V initial is 35 meters per second. And then I divide it by T, 0.25 seconds. So 35 divided by 0.25, that is 140. With that negative sign in front, because it's 0 minus. And the units, meters per second squared. What does the negative sign indicate? What's going backwards? Of what? Of the acceleration, not of the velocity, because the velocity is sort of positive the whole time, but it's decreasing until it turns into 0. So velocity and acceleration are in opposite directions. Yeah.
In the homework, it asks you to make graphs that are velocity versus acceleration, right? So it'll say like the acceleration is positive and the
Initial velocity
is negative, right? Or like the other way around.
Let's do this. Let's do this one as that graph. So we have the initial velocity is a positive and the acceleration is a negative. Okay? So here would be the graph of velocity versus time. Okay? So if the initial velocity is positive, then our graph needs to start with a positive intercept, and it needs to have a positive slope, negative slope, or 0 slope. Negative slope. The acceleration is negative. The slope of a velocity versus time graph is the acceleration. So this is what this graph would look like if we want to do like a graphical solution for this. And the way it grades it, it doesn't care where you start it as long as it's positive. And it doesn't care what the number of the slope is as long as it's negative. So there's more than one answer to this question. This would also be positive initial velocity and negative slope.
But wait, like I don't understand why you said that acceleration is like concavity and
For a position versus time graph. For a velocity versus time graph, it's slope. That's the difference. Okay. So here's what we're going to do for the last 15 minutes of class. Okay. So I'm going to give each table a different question it's a kinematics question. So it's similar to what we've been doing. And at your table, you're going to use the computer to make a slideshow and to write the words that you would say. And you can get those links on the website. I'm going to go post it on Google Classroom right now. Yes. So you will have a template that has a spot where you type the question, where you do I've already made all the equations that you might want to use, okay? And then you're going to submit your slides and your script using a Google form. Okay? Hold on. Yeah. Okay, so you should be able to click the links on it should be updated now, hopefully. So if you click the link, like this will click here, right? Right, and then you'll make your own copy. That right there. Okay, so this is what the slides template looks like. I've got instructions written in the bottom. Okay, so you can grab any of the equations you might want to use. I've already solved it. You're going to type the question, and then you're going to use animation to make your solution. And then for your scripts, same thing. You make makes a copy when you click on it. Make a copy. And you have the place where you would write the words that someone in your group is going to say. Again, I have directions here. Okay. And then finally, you submit all of that using the Google form. So let me hand out the questions to each group, and then I'll answer questions that you might have. And I will post the link to the website on Google Classroom. So if the links aren't working for you, let me do that first.